Hi guys, in the last lecture what we covered is we first saw the basics of the transformer, then we saw what kind of core material do we use. So we saw that we generally prefer materials which have high permeability and low reluctance. Why is it so? So that the most of the flux is confined to the core. Then we saw the most commonly used material is silicon steel. But further we use the CRGO steel, which is an improved version of silicon steel, so that permeability is increased in the direction of magnetization. Then we saw that we generally use laminated core. Why we use laminations? So that we can reduce the eddy current losses, and we use insulators between the two laminations. Then we saw shape of the core, that is the core type of transformer, and shell type of the transformer. We saw that core type was preferred for high voltage low current rating and shell type was preferred for low voltage high current rating. Then we saw ideal transformer. We saw what are the properties or the assumptions when we consider an ideal transformer, like it must have infinite permeability, that it must have zero iron losses, it must have zero leakage flux, it must have zero winding resistance, and the magnetization curve should be linear. Now in this lecture what we will do is we will remove those assumptions one by one and try to construct the model for the practical transformer. So the first assumption of an ideal transformer was mu is equal to infinity. So now we will consider the transformer where permeability is not infinite but a finite number. So if we consider the finite permeability, we will consider a current I mu, which is my magnetizing current. Okay, magnetizing current means the current required to create the magnetic field or the magnetic flux inside the core. That is my magnetizing current, that is represented by I mu. Now usually we apply sinusoidal source. So I will say I mu is Im sin omega t. So we can find MMF for the primary winding is N1 into I mu, which is N1 Im sin omega t, or we can call it as phi m sin omega t. Phi m is the maximum value of flux inside the core, which is, sorry, not phi m, this will be Fm. Okay, now we can find flux is Fp by reluctance. MMF by reluctance will give me flux, so it will be phi m sin omega t. Phi m is the maximum value of flux inside the core, Fm is the maximum value of MMF inside the core. Now to find out the EMF induced, we can use the Lenz's law. Lenz's law is EMF is equal to minus d phi by dt into number of turns. So if we are finding the primary EMF, we will take N1 number of turns. So it will be minus N1 phi m cos omega t into omega, that is minus N1 phi m omega cos omega t. If we want to write this in terms of sin omega t, what we can write out? EMF is equal to N1 phi m omega sin omega t minus pi by 2. Okay, see, now if you observe that the flux was phi m sin omega t, but EMF is sin omega t minus pi by 2. That means induced EMF lags the flux by 90 degree. So if we represent flux in phasor form like this, if this is my flux, then EMF will be lagging by 90 degree, that is 90 degree clockwise. This is how we will represent the flux and EMF in the phasor form. Now if you see, maximum value of EMF is N1 phi m omega. So RMS value will be N1 phi m into omega, that means 2 pi f divided by root 2. So it is 4.44 N1 phi m f. This is what the EMF induced in the primary winding. So this expression is very important. This you must always remember. This will be used in synchronous machines as well as induction machine. So induced EMF is 4.44 F into number of turns into maximum value of flux inside the core. So remember, RMS value of EMF depends on maximum value of flux. So this is all about primary. Now let us see further. What we can do is we can break this flux into flux density and area. So we can write RMS value is 4.44 F N1 Bm into An. An means normal area to the magnetic field, or we can say cross section area. Bm is the maximum value of magnetic flux density inside the core. So what I have done is I have converted the flux into flux density. Now similarly, if we were finding about the EMF in the secondary winding, what we will do? Minus N2 d phi by dt. So it will come out to be N2 phi m omega sine omega t minus pi by 2. Okay. So what we can write down, E2 RMS will be nothing but 4.44 F N2 phi m. Okay, just remember, in the EMF expression between primary and secondary winding, what changes is, the only thing that changes is the number of turns, because as per Lenz's law, EMF is directly proportional to the number of turns. So what I can say is E2 by E1 is equal to N2 by N1. The ratio of EMF induced in the primary and secondary winding is same as the ratio of number of turns. This is a very important concept, or one of the first concept that we study in the transformer. That is how we can use the transformer as step up or step down. For step up transformer, what we will do is output voltage or secondary voltage must be greater than primary. It implies secondary number of turns must be greater than primary number of turns. Similarly, if we wish to use it as step down, that means output voltage must be less than input, E2 must be less than E1, that means N2 must be less than N1. So that is how we can use a transformer as a step up or a step down transformer. Now if we wish to draw the entire phasor, the reference that I will be using will be my flux, or what we can do is magnetizing current. We took magnetizing current as I mu, which was Im sine omega t. Okay, and we saw that the flux was also phi m sine omega t. That means flux and the magnetizing current are in the same phase. So this concept you must always remember. The current producing the flux and the flux produced will always be in the same phase. Again I am repeating, the current and the flux produced by the current should be in the same phase. So what I will represent here is phi. Now we saw that the induced EMF in primary and secondary winding was lagging the flux by 90 degree. So here I am representing E1 and let us represent E2. So here I have shown E2 is greater than E1. That is just an assumption. That is what I am considering a step up transformer. That is why length of E2 is greater than length of E1. Now what we do is the applied voltage. Applied voltage is shown like this. V1 is equal to minus E1. Why it is shown like this? To satisfy the Lenz's law. As per Lenz's law, induced EMF must always oppose the cause of induction. Here the cause of induction is the primary voltage that is connected in the primary winding, or the supply voltage that is connected to the primary. So induced EMF must be opposite to that voltage. That is why we write V1 is equal to minus of E1. Okay. So that is how we draw the phasor basic phasor diagram of a transformer. Is it fine? Now let us make some observations from whatever we have studied. First of all, we saw E2 by E1 is equal to N2 by N1. It is equal to K, which is called as transformation ratio. Okay, that is the ratio in which the voltages are transformed from the primary to the secondary winding. Now, maximum flux density inside the core is directly proportional to E by F. As we saw, EMF was 4.44 FNB. Okay, so maximum flux density was proportional to E by F. Okay, or we can say V1 by F. So this is very important relation, because this will appear many times in the due course of the electrical machine, that even in induction motor generally the speed control method used is constant V by F control. So constant V by F means constant magnetic flux density. So this you must always keep in mind. Now suppose if voltage is kept constant and we reduce the frequency, then what will happen? V by F will increase, which will lead to increase in the magnetic flux density. Now if magnetic flux density keeps on increasing, it may push the transformer into the saturation region. So if the transformer enters the saturation region, what happens? If we see the curve, let us say B versus I mu, the curve may be something like this. If suppose if this is Bm, this is 2 Bm, then the change in magnetizing current is more than the change in field, I mu 1, I mu 2. So actually I mu 2 is greater than 2 times I mu 1. Why is it so? Because of the saturating nature of the curve. If the curve was a straight line, then the ratio of change in y will be same as ratio of change in x. The same sort of relationship will exist in the x. But the thing is, curve is not linear. So the increase in magnetizing current is pretty large. And as I told you, why magnetizing current is undesirable? Again and again I am telling, magnetizing current is undesirable. It will damage the power factor of the machine. That is why we do not desire the magnetizing current. That is why I was assuming that ideal transformer has infinite permeability. Infinite permeability signifies zero magnetizing current. Magnetizing current always worsens the power factor of a machine. So here the magnetizing current will increase immensely and power factor will be worse. Now usually kVA rating of the transformer is directly proportional to the frequency. Because my voltage rating depends on the frequency, current rating does not depend on the frequency. So kVA rating will depend on frequency. So kVA rating of the transformer is directly proportional to frequency of operation. Next is this magnetic flux density Bm. It depends on the type of material. That is, for CRGO steel, it is approximately 1.2 up to 1.6 Tesla. For silicon steel, it is approximately 1 up to 1.2 Tesla. This is the range of the magnetic flux density for the different type of materials that we can use. Now the thing that you must remember, Bm is inversely proportional to the weight of the transformer. Higher the magnetic flux density, lower is the weight of the transformer. That is what you must always remember. Secondly, at high frequencies, the size and the weight of the transformer will also reduce. Okay, so high frequency transformers or high frequency devices are smaller in size, as well as the higher the magnetic flux density, the lesser is the size and weight of the transformer. Okay, So remember this, Bm is inversely proportional to weight and size of the transformer. So this is what happens when we take the finite permeability. What is the effect? Finite permeability induces a magnetizing current in the primary winding. It draws a current from the source to develop the flux in the core. That current is called as magnetizing current. Next, let us remove the other assumption, that is zero iron losses. So what I am considering is there are some iron losses in the transformer. Iron losses refer to the losses that occur in core of the transformer. Okay, since the core is made of steel or iron, these are called as iron losses. Now there are two type of iron losses usually: hysteresis loss and eddy current loss. Now, as many of you very well know that iron loss or any other loss for that matter consumes real power. The difference between real and reactive power is real power is actually useful power or the power that can be dissipated. Reactive power is the energy stored in the system. So, any sort of loss is concerned with the real power. Now, usually real power is Vi cos phi and reactive power is Vi sin phi. Now, if you observe, since the losses must consume only real power, so in loss reactive power must be 0. That is, the angle must be 0. So angle between the voltage and current due to losses should be 0. That is, the voltage and the loss current must lie in the same phase. Current due to losses, what I am referring to is whenever there are losses in the system, where will that losses be supplied from? Those losses will be supplied from the source. So the source will deliver a current which I am calling as loss current. There are certain losses in the transformer, and to compensate those losses, the source will have to supply some current that is called as my loss current. And remember, the voltage applied and the loss current should always be in the same phase, because losses consume only real power and no reactive power. If you see just now, I drew a phasor I mu and applied voltage. So here if you see, there was 90-degree angle, so real power would be 0 and reactive power would be V into I mu. That means to develop the flux, reactive power should be consumed. That is why in any system reactive power is indispensable, because all my electrical machines require flux to work upon, and flux developed is through a magnetizing current, and to develop magnetizing current we need reactive power. Okay. So why reactive power is necessary inside any system? Because reactive power must be consumed to develop the flux in a system, and for compensating the losses we use real power. So for losses reactive power is 0 and for flux development real power is 0. That is why we can never reduce the reactive power to 0, because if we reduce reactive power to 0, there will be no magnetizing current and hence there will be no flux, and without any flux none of the electrical machines can work. Okay. So now, since I am saying that the losses will draw some current from the source, the losses will require some current from the source. That current I will represent by IW. IW means watt component of the current. Watt is the unit of real power. That means this IW is related to the real power. That is why we are calling it as IW. And usually I mu is much greater than IW. So now if you see, we have two currents. One current is being drawn from the supply to generate the flux, that is called as magnetizing current, and one current is being drawn from the supply to compensate the iron losses, that is called as loss component of the no load current. Why no load? Because we haven't connected any load on the secondary side. So without any load, some current is being drawn from the primary. So some of these two current will be called as no load current of the transformer. But the thing is, IW will lie in the same phase as the voltage. I mu will lie in the 90 degree to the applied voltage. Usually the no load current is how much? 5 to 8% of full load current. Okay. So no load current is always around 5 to 8% of the full load current. So it is very small in value for the transformer. Now let us see how we can represent in phasor form both this magnetizing and the loss component of the current. So first of all, what we draw is, we draw the magnetizing current, then in the same phase we draw the flux. Then 90-degree lagging, we have the two EMFs being induced, E1 and E2. Then we say that V1 will be equal to minus E1 to satisfy the Lenz's law. Now, as I told you, there is an additional current in the same phase as the applied voltage, which is IW. So IW will lie in the same phase of the voltage so that it consumes only real power. Now I told you the sum of IW and IMU will be called as no load current because these are being drawn from the supply even under no load condition. So how to take the sum? We will take the sum something like this. This will be I naught or the no load current in case of transformer. Is it fine? Now this angle phi naught is called as no load power factor angle, and cos of phi naught is called as no load power factor. Okay, that is no load power factor, and it is almost 0.2 lag. No load power factor is around 0.2 lag. Now what happens is, suppose if we keep the voltage constant and we reduce the frequency, then as I told you, Bm is proportional to V by F. Bm will increase because frequency is being reduced, which will lead to increase in magnetizing current. So increase in magnetizing current will lead to increase in phi naught and reduction in the no load power factor cos phi naught. Cos phi naught will reduce, no load power factor of the machine will go down. Okay, and no load losses or the iron losses will be given by V1 into IW. This is what is equal to iron losses or the core losses in the transformer. Okay, so power consumed by the transformer at no load is used to supply the iron losses, and reactive power drawn from the supply is used to generate the flux inside the transformer. Now let us see how we can model it in terms of electrical circuit. We will draw electrical circuit like this. R0 is my core loss resistance. Actually, there is no such resistance as the core loss resistance. This is a hypothetical resistance. It is just used to represent the core losses or the iron losses in a transformer. Okay. So since if you see IW current is going here, the power in the R0 will be V1 into IW. This is same as the iron losses as I told you earlier. Now we saw that the I mu lags voltage by 90 degree. So current if lags by the voltage by 90 degree, that means it is passing through an inductor. So we show a magnetizing reactance. X0 is called as magnetizing reactance. Okay, this is just being shown as a reactance because we see magnetizing current must lag the voltage by 90 degree. So we have shown it by purpose of by means of a inductance, because in an inductor current always lags the voltage by 90 degree. Now sum of these two current will be my no load current I naught, and we have shown the secondary winding open circuited. That means no load condition. So this is the no load equivalent circuit of the transformer. In no load equivalent circuit, we consider two parameters. One is the core loss resistance, and the power in that core loss resistance gives me the value of iron losses. Other is the magnetizing reactance. The current through the magnetizing reactance is called as magnetizing current, which is used to develop the flux in the core of transformer. Okay. Now let us see what happens to this model or what will happen to the current being drawn from the supply if we connect a load on the secondary. Till now what we are considering is there is no load on the secondary winding. Now let us consider a load. So what I have done is I have connected a load Z1 here. So what happens? Now earlier only the EMF was being induced in the secondary winding due to the flux. Now since you have connected an impedance, what will happen? A current will also flow through the secondary winding, which is being represented by I2. I2 is the current that is flowing through the secondary winding, and as I told you in Lenz's law, the purpose of the secondary flux is to oppose the primary flux. Induced EMF or induced current opposes the cause of induction. Cause of induction is the flux generated by the primary winding. So secondary flux will try to reduce the primary flux. Okay. So earlier what was happening is we had primary MMF under no load condition was N1 into I mu. Now what happens? Secondary MMF also comes. Secondary MMF is N2 into I2. This secondary MMF, what it tries to do is it tries to reduce the primary flux. So to change that or to oppose that, okay, since it is trying to reduce the primary flux, what primary winding does is it draws an additional current. Okay, it asks the supply for an additional current to cancel this secondary flux or the secondary MMF. Secondary winding is cancelling the primary flux, so primary flux will increase itself to compensate for the secondary flux. So primary winding draws an additional current I1 dash. The purpose of this I1 dash is to cancel secondary MMF. It must cancel secondary MMF. Therefore, N2I2 will be equal to N1 I1 dash. That means I1 dash by I2 is equal to N1 N2 by N1. Okay. So I1 dash is usually called as load component of the primary current. Why is it called as load component? Because it is generated only when a load is connected across the secondary winding. So it is called as load component of the secondary current. So load component of the primary current and load component of the secondary current are related by the inverse of the turns ratio. Now since primary is cancelling the secondary MMF, the only MMF that remains is N1 into I mu, because these two MMFs will cancel out each other. So we can say the MMF in the transformer is constant or the flux in the transformer is constant. So transformer can be treated as a constant flux device. Okay. By constant flux device, do not confuse that the flux is constant actually. The thing is the magnitude of the flux will be constant or the amplitude will be constant. Flux will be sinusoidal but its amplitude will be constant. Why is it constant? Because net MMF is N1 I mu plus N1 I1 dash minus N2 I2. Now these two get cancelled, so net flux or net MMF is always N1 into I mu. No matter what load you apply, I2 will change, but at the same time I1 dash will be induced in such a manner that it cancels the secondary MMF. That is, based on the secondary current, primary current will be induced. So the thing to observe here is, whenever we are talking about induction of voltages, the voltage is induced from the primary winding to the secondary winding. We are applying a primary voltage, that is why voltage is induced in the secondary winding. But in case of current, since there is secondary current, therefore the current is induced in the primary. So current is induced from the secondary to the primary, voltage is induced from the primary to the secondary winding. So voltage goes from primary to secondary and current goes from secondary to primary. This is how current and the voltage transformation takes place. Now as we just saw, N2 by N1 is equal to I1 dash by I2 is equal to E2 by E1. N2 by N1 was equal to voltage ratio. So what we can say is E1 I1 dash is equal to E2 I2. So the load power on the primary side is same as load kVA on the secondary side. Load kVA on primary is equal to secondary kVA. That means the apparent power due to load current on the primary is equal to apparent power on the secondary winding. Now we have seen three type of current in the primary winding. What three type of current? One is I1 dash that we saw just now. One was I mu. One was IW. Now these are collectively called as no load current. So effectively we have two currents in the primary winding, I1 dash and I0. So the sum of these two current is called as I1, which is the primary current. Now if we neglect the no load current, because the no load current is usually 5 to 8% of the primary current. So if I0 is considered to be 0, I1 will be equal to I1 dash. Then we will say E1 I1 is equal to E2 I2. Primary kVA is equal to secondary kVA. Okay. Now let us draw the phasor diagram of the transformer under the loaded condition. So we will start from the basic itself. We will first draw magnetizing current. Then we will draw flux. Then EMF will be induced E1. EMF will be induced E2. Okay. The voltage V1 will be equal to minus of E1. Now, since we have connected a load across the secondary, there will be some load current I2, and I am assuming that the load that we have connected is lagging power factor. It is lagging the voltage by a power factor angle phi 2. The load that we have connected across the secondary winding is lagging load. Now, primary will draw an additional current. How much additional current? If you see here, I1 dash is equal to N2 by N1 into I2, which is equal to K times I2. K is the transformation ratio. So primary will draw current KI2, which will oppose the secondary MMF or secondary flux. So to show the opposition in the phasor diagram, what we do is we draw the opposite phasors of both the currents. So it will be like this, K I2. Okay, and we will have one current IW, which is the loss component of the current, and this will be my I0, no load current. Now, first thing that you must remember, whatever we are showing in phasor is not true when it comes to numerical problems. Why? Because the thing is, both secondary and the primary MMFs will oppose each other based on the winding orientation. But in phasor diagram, to show the opposition of MMF, we draw the currents in opposite phase. Okay, what I am telling is, suppose this is my transformer. Okay, so current here will be entering, current here will be leaving. The flux due to this, if you use the right hand thumb rule, will be clockwise. Okay, it will be clockwise. And current due to this winding will be anti-clockwise. It will be upward. So here if you see, both the fluxes are opposing each other. In this limb, the current flux, first flux is like this, other is like this. One is clockwise, other is anti-clockwise. That means the fluxes are opposing each other, though the currents may be in same phase. So actually the opposition in the MMF or the flux comes from the winding orientation. It has nothing to do with the phase of the current. But in phasor diagram, we cannot show the winding orientation. So what we do is, we draw both the phasors in opposite direction to satisfy the Lenz's law, or to show that both MMF try to cancel each other. So whenever you are doing the numericals, you will take I1 dash and I2 in same phase. Okay, because the opposition comes from the winding orientation and not the phasor or the phase of both the vectors. So remember this. Now if we want to find the total primary current, we will add these two current. something like this. Here I will get I1. This is my primary current, and this angle phi 1, this cos of phi 1 will give me primary power factor. Cos of phi 2 is secondary power factor, and if we take phi naught, it will give me no load power factor. If you take the angle between V and I naught, will give me no load power factor. Okay, so remember this, whenever we will be doing numericals, we will take I1 dash and I2 in the same phase, because they will be cancelling each other due to the winding orientation. They may not be in opposite phase, but in phasor diagram we will always represent them in opposite phase. Why? Because we want to satisfy the Lenz's law and we want to show the cancellation of MMF. So let us summarize what we learnt in this lecture. First we saw the effect of finite permeability. What we saw, that induced EMF is 4.44 Fn Bm into An. This was the EMF equation for the transformer. For primary we will take E1 and N1, and for secondary we will take E2 and N2. So we saw E2 by E1 is equal to N2 by N1. Then we saw next was core loss, which was represented by a current IW, and under root IW square plus I mu square will give me I naught. Then we saw the no load equivalent circuit, and at last we saw loaded transformer, in which we saw primary and secondary MMF cancel each other. N1 I1 dash was equal to N2 into I2, and primary current was I1 dash plus I naught. This was the net primary current. In the next lecture, we will remove some more non-idealities, that is the winding resistance and the leakage flux, and come up with a model of a practical transformer. That we will cover in the next lecture.